Lab 1 Charge Tapes by Shervin Praveen. Introduction. The purpose of this lab is to measure and model the transfer of electrons between two pieces of tape. We will then see how the charged tapes interact with each other. To model this experiment, we will be using GlowScript. We learned that we are able to accurately find the charge of the tapes using this modeling technique. The fundamental principles we will be using are Newton's second law, which state that F net equals ma. In our experiment, we notice that our top piece of tape is not moving, so when we set acceleration equal to 0, we notice that F net equals 0. We will also be using Coulomb's law, which is used to find the interactions between two particles with different charges. Experiment. During the experiment, we will look at the top piece of tape as the system, and the bottom piece and the earth as the surroundings. When we pull the tape apart from another piece of tape, the U-tape ends up being negatively charged. As you can see in the picture, there are two U-tapes which are both negatively charged. Initial conditions. The lengths of the piece of tape were 20 centimeters or 0.2 meters. The mass is around 0.2 grams or 0.0002 kilograms. The final conditions. The distance between the tapes was 1 centimeter. We know that F net equals 0 since the top tape is not moving, and if the top tape is not moving, then there are equal forces. There's gravity pointing down, so we notice that the force of electricity is equal and opposite pointing upwards. Coding. For part 1, we model the forces acting on the top piece of the tape. In this code, we assume that the tape is a single point charge and find the charge of the tape. For part 2, we model the forces acting on the top piece of the tape by distributing the total charge evenly across the length of both the tapes. Similarities, differences, and sources of error. Our model is decently accurate compared to the experiment. There are some sources of error that could make some differences. For part 1, we assumed the tape was a point charge. We also assumed the distance of the forces was from the center to the center. Both of these assumptions are not entirely accurate. For part 2 of the lab should be more accurate, but not entirely perfect. We did have to assume that internal interactions could be ignored. We also only modeled a finite number of charges, in our case 10 for visualization. Questions. Magnitudes of charges in single versus line. To reach F net equals 0, with our code, we see that the required single point charge is negative 4.76 times 10 to the negative 9. But the required charge for a line of charges is negative 1.372 times 10 to the negative 8. Is the U-tape positively or negatively charged? Negative. This can be proved by noting the repelling motion of the tape near a pen rubbed on hair, which is known to be negatively charged. Can we assume that the tape has the same net charge? If a tape is neutrally charged and we pull one from the other, the charge will be the same magnitude but the opposite sign. What if the signs of charges were reversed? If the charges were reversed, then the electron transfer would make both of the U-tapes positively charged instead of negatively charged. The results will mostly be the same since the tapes are both the same charges. Right now we have two negatively charged U-tapes, but in that case we'll have two positively charged U-tapes, and they'll still levitate like they did in this one. The only difference would be that the electric field would point in the opposite direction, and the charges would be positive instead of negative. Why are the two estimated Q's different? There are two different values for Q because the line charges account for diagonal charges as well as vertical. This means the second Q would be more accurate since it accounts for the distances in the horizontal direction and how that affects the forces. Thank you.